So hello everyone. Again, this is Sir Don and we are going to illustrate systems of linear equations into variables. So in this lesson, we will be dealing with several equations being drawn in a Cartesian plane, and we're going to look at some behavior that we can see in the given graph or equation. Our objective in illustrating system of linear equations into variables is that you should illustrate linear equations into variables. So these are the important terms that you will be encountering while we have this discussion. So the first one is what we call the systems of linear equations. This is also called the simultaneous equations. So this is a set or collection of linear equations, all of which must be satisfied. Okay, this one is an example of systems of linear equation into variables, since both are linear equalities. As you can see, this one is a linear equation, this one is also a linear equation. So it has two variables and this one has two variables. And these two equations are also called simultaneous equations. So this is not an example of systems of linear equation into variables since it is only one equation. When we say system, it should be a set or collection of linear equations. It should not be alone. It should not be only one. The next one is not also a system of linear equation into variables, though it contains two variables. However, the second one, which is 3x minus y is greater than 8, is not an equation. This is a linear inequality because of the presence of the greater than sign or symbol. And last one is that not also an example of systems of linear equation into variables, since you have here 2x plus y plus z equals 5 has three variables. So we are just going to focus with a linear equation containing two variables. Okay, the next term that we're going to focus with is what we call the solution. So this is the coordinates of all the points of intersection of the graphs of the equations in the system whose coordinates must satisfy all equations in the system. Here in the systems of linear equation is that we're going to graph several equations in one Cartesian plane, and we're going to look for the point of intersection, and that point of intersection will satisfy the two or more given equations. So that point of intersection, this is what we call a solution. This is a solution, or simply a point that will satisfy the name of this line and the name of this line. The next one is what we call coinciding lines. So simply this is an overlapping lines, wherein in this illustration we have a line here, a line, and another line overlaps the previous line. So these are two lines that coincides, or these are overlapping lines. So if these two lines intersect at several points, therefore there are many solutions that are present here in these two lines. The next term is very common to us because this is what we call the intersecting lines, or simply these are lines that meet at exactly one point. So in this one, we have here a point 1, 3. This is what we call the point of intersection of these two different lines. So these two lines are intersecting lines. Next one is what we call parallel lines. These are coplanar lines that do not intersect. So when we say coplanar lines, these are two lines that are present or drawn on a similar plane, on the same plane. So when we say parallel lines, these are coplanar, or lines that are drawn on the same plane and they do not intersect. So there is no solution, or there is no point of intersection, because if you're going to extend this opposite sides of these two lines or opposite directions, there will be no such case that these two lines will intersect. So that is why these two lines are parallel lines. The next one is what we call consistent and independent system. So these are lines that meet at exactly one point. So if you're going to refer to this one to the previous topic, this is what we call intersecting lines since they meet at one point. The slopes of the lines defined by the equations are not equal. Their y-intercepts could be equal or unequal, and their graphs intersect at exactly one point. So this one is an example of consistent and independent system. This is composed of intersecting lines, and the slopes here are different as well as the y-intercepts. So if the equations are given. The next term is consistent and dependent system. This is a system of linear equation having infinitely many solutions. Where the graph here is actually an overlapping lines, so it has infinite number of solutions. So the slopes of the lines defined by the equations are equal. So the slopes here are the same, and their y-intercepts are also equal, and their graphs coincide. So these are actually identical equations. The last term that we are going to discuss is what we call the inconsistent system. This is a system of linear equation having no solution. So the slopes of the lines defined by the equations are equal. So the slopes are the same. So if the slopes are the same, so again the lines are parallel. So their y-intercepts are not equal and their graphs are parallel. Okay, for you to be familiar with the terms that we have discussed, so let's have a summary of the concepts. So the first column is the type of line or graph. The second one is the type of system. Then the third one is the number of solutions. Then we have a sample equation and then the characteristics on the last column. Okay, the first one is what we call the intersecting lines. So the graph of that is this one. So we have here a point of intersection. So this graph is consistent and independent system. So when we say consistent and independent, there is one solution. Why one? Because there is one point of intersection among intersecting lines. So let's say for instance, we have a sample equation here, y is equal to x plus 3, and we have y is equal to 5x plus minus 1. Because the characteristics of this one, two lines will intersect if their slopes are different, as well as the y-intercept, or the y-intercepts there can be equal also. As long as their slopes are different, so these two lines will intersect. The next one is coinciding lines or overlapping lines. So these are overlapping lines. This is a consistent and dependent system. So the number of solutions is infinitely many. Infinitely many because we have here several points of intersection. If the two lines overlap, there will be a infinite number of solutions, or there are infinite number of points of intersections. Just like this one, we have y is equal to 3x plus 6, then 2y is equal to 6x plus 12, because if you're going to simplify this one, it will give you y is equal to 3x plus 6. Because the property of two lines that overlaps, their slopes are equal and the y-intercepts are also equal. And the last type of line or graph, we have here parallel lines. This is an inconsistent system. As you can see, two lines here are parallel. There is no case that these two lines will intersect. So that is why there is no solution, because there is no point of intersection. Sample equation, we have here y is equal to 3x plus 1, and then y is equal to 3x minus 5. Because if the two lines have the same slopes, although the y-intercepts are different, these two lines are parallel. So that is the summary of the concepts that we have tackled. For you to understand the topics that we have discussed, so let's have this learning situation number 1. So you're going to tell whether the given illustrates a system of linear equation in two variables or not. So you're going to judge if the given equation or pair of equations is a system of linear equations in two variables or not. So if that is a system of linear equation in two variables, then you're going to describe the number of solution, the graph, and then the type of system. Okay, so let's have the first one. Y is equal to 2x minus 5, and then y is equal to 5x plus 5. So this braces, this symbolizes that these two are working simultaneously, or this can be solved. These are paired. This can be solved simultaneously. Okay, so this is a systems of linear equation in two variables because both are linear equalities. As you can see, these have two variables x and y, and these are also both linear equalities. Then the graph of this system is an intersecting lines. Why? Because the slopes are not equal. So the slope in the first equation is 2, the other one is 5. So take note that these are not equal, so we have here an intersecting lines. Since they are intersecting lines, so it has one solution. Since the graph is an intersecting line, so it has only one solution. So since there is one solution, therefore the type of system is consistent and independent system. Problem number 2. So the given is 2x plus 3y is equal to 1. And then the second equation is y is equal to negative 2/3 x plus 2. So this is also a systems of linear equation in two variables because both are linear equalities. Then the first equation can be expressed as y is equal to negative 2/3 x plus 1. So by expressing this one, the first equation, which is 2x plus 3y equals 1, by expressing this one in y form, or that is slope-intercept form, so this one is equivalent to y is equal to 2/3 x plus 1. Since the slopes are equal, therefore their graph is a parallel line. Since this one is a parallel line, therefore there is no solution. And since there's no solution, so this is an inconsistent system. Okay, so our last example, we have here 2x plus 3y equals 1, and then we have 6x plus 9 is equal to 3. So it has two variables, and also this is a linear inequality. So therefore, this is a system of linear equation in two variables. The first equation can be expressed as y is equal to negative 2/3 x plus 1, and the second equation can be expressed as y is equal to negative 2/3 x plus 1 if that is simplified. Since the slopes here are equal and then the y-intercepts are identical also, then the graph of this system is coinciding or overlapping. Since this one is an overlapping line, so it has infinitely many solutions. And since there are infinite solutions, this is a consistent and dependent system. So I hope that you learned something for this. So out of the given equation, you can predict some of the important properties or characteristics of the possible graph of the systems.